vortex contains some of the coldest air on the earth. So the air is often contained by a strong jet of west to east moving winds, right? West to east moving winds that act like a wall, right? So containing the cold air. So these winds move at more than how many kilometers? 161 kilometers, right? 161 kilometers or 100 miles. Okay, or 100 miles per hour. Per hour. So which help lock the air into place. So the vortex in the northern hemisphere is believed to have two centers. So one is in northern Canada near Baffin Island, and another one is northeastern Siberia. So the southern hemisphere polar vortex is usually centered around the south pole, right? So occasionally it changes in air pressure and wind. It helps to diminish the like wall, right? Wall of containing the polar vortex and causing bubbles within the vortex. So though and this unleashes cold air from the pores, it allowing it to spread to other regions, right? So this results in temperatures plummeting below how much minus, right? Minus 18 degrees centigrade in major cities, right? So in, for example, in the United States, the weekend vortex can cause bitterly cold temperature to reach as far south as Florida, right? So the Arctic's polar vortex is stronger than its northern counterpart and not as susceptible to these bubbles, right? So now we are going to briefly about this polar vortex, right? So you see, these are two words, right? First one is polar and second one is vortex. This one polar and second one is vortex, right? So what is this vortex first of all? So all about and where it is coming from. So now vortex is basically this whirling action, right? Like this whirling action. Or it means something which moves in a this circular motion. Okay. So for example, whenever you take lots of water in a bucket or your kitchen sink, you can try and you keep whirling, right? Whirling it. So what happens is there, this whirl created, right? So this is a wide wind or whirlpool. So that is created even your washing machine also you can find it out. So that is called vortex, right? So what is vortex? It's a whirling action. So now what is this whirling action and how it is related to polar areas, and that is where this creation of polar vortex happens. Now you see here, so vortexes were polar. What is polar? Polar means, which means anything related to this north and south pole, right? North and south pole. So let's understand this concept in terms of this entire climatology and its impact on the entire climate system, right? So now you see here, the polar vortex is a largely area of, what is that? Low pressure and cold air. So now the first line itself, it seems to be very contradictory. So that low pressure is associated with, what is that? Warm air, right? Low pressure is associated with warm air. So what is this? So this is low pressure and cold air, right? So how it can be, so let's understand, and it is basically where the area itself is clear, it is the polar area. So it will have cold air itself. So, but why this so low pressure? Then it's so let's understand and clarify this point. That is that it is a low pressure area, right? So, but it is cold area surroundings the Earth's north and south poles, and this is referred to as the polar vortex, right? So now you see this picture. So actually, there are two vortices on the Earth or a globe, right? So first one is, this is first one, and this is second. So what is the first one? First one is Southern Hemisphere. So it is in over the Antarctica. And second one is Northern Hemisphere. It is over the Arctic region, right? So the Northern Hemisphere polar vortex is the strongest one, right? So the Northern Hemisphere is about how much? 60.7% of water and 39.3 is land. And in Southern Hemisphere is about how much? 80%, 80.9% of water and 19.1% of land. So the term vortex basically is what? It is clockwise or counterclockwise. It is depending upon the Northern Hemisphere, that is over Antarctica region, and Southern Hemisphere over the Arctic, right? So in Northern Hemisphere, it is anti-clockwise, right? Anti-clockwise, like this. And Southern Hemisphere, it is clockwise, right? It is clockwise. So this kind of wind movement, very fast wind movement, happens at the poles, specifically in the stratospheric belt, that is upper atmosphere, right? So what happens? Now you see, often during winter in the Northern Hemisphere, remember it is the winter, right? In Northern Hemisphere, when we say, it means sun movement is southwards, right? Sun movement is southward. One second, sorry. So this oscillation, that leads to this, right? So the polar vortex becomes less stable and expands. So, and further, if we say, if this expands, what will happen? This cold air, right? This cold air will come to these land areas, right? Land areas. And it will bring lots of chilly winters and negative temperatures. Okay. So this is why it was a concern for many of the countries like Canada or US, right? So that this keeps happening in certain years where there is this polar vortex migration to these land areas, right? These land areas. So this is important. So that how this entire polar vortex is formed and how it functions, why this is important, right? So it is new concept? No, right? Is it new concept? No. So first time it was discussed even in as back as in the year of, you see here, 1853 in an article that is living age, right? That is living age, where it was discussed as a fact that this also happens. So this kind of phenomena is there. So where you have upper atmospheric circulation, which is kind of whirling wind. So which is there at the pole, right? So now So now let's discuss this in terms of the conceptualization and formation. So now you see here, now so many years, right? Now so many peoples, it get confused. What? So that how this low pressure system is formed in polar regions, right? So that is the question. So now you see here. So why this polar vortex is created as low pressure system, and how even if there's so much of cold air, what is the reason? So now let's understand what happened is here. So if you observe what is happening, this is the line which is called a tropopause, right? Like this line, this red line is, sorry, yellow line is uh, tropopause, right? So which is about how many kilometers? Here, you see here, this one, maybe 12 to 15 kilometers, right? 12 to 15 kilometers. So, and it is the dividing line between, where is that? A troposphere and a stratosphere. I already told about the what is the troposphere and tropopause and mesopause, right? So where it is tropopause, so that is between the troposphere and stratosphere, right? So the polar vortex starts at the upper troposphere and it extends into the stratosphere, and sometimes it continues up to the mesosphere also, right? So what happens, this height continuously keep going down as we go towards the uh, pole, right? Towards the pole. So at the pole, the tropopause, this is the tropopause. Tropopause is about how much kilometers? 8 kilometers, right? 8 kilometers. So that is between 7 and 9 kilometers, right? And it is maximum about 15 kilometers at the equatorial line, right? Equatorial region. So that is the basic idea. So basic structure, right? So now, what happens? The air from the this you see here this ferrule cell and polar cell and Hadley cell is there, right? Ferrule, polar, Hadley, right? So this ferrule cell and the polar cell. So this is where it is you see here. Eastern and westerlies, right? Easterlies and westerlies. You see this one, easterlies, westerlies. This is easterlies and westerlies. So meet at this junction, right? So that is, sorry, this one. So that is 60 degrees, right? 60 degrees north. You see here, 60 degrees north. So this is called, what is that? Polar uh, front, polar front. So, and also what you find there, that is polar jet stream, it created, right? Polar jet stream is created because of this mixing of warm and cold air. So what is the polar jet stream? So what is polar jet stream? So the polar jet stream and polar vortex are two rings, right? So two rings of fast moving air around the Arctic. So which plays a large role in the world weather patterns. So many climate scientists believe that the global warming is changing these rings. So in ways that allow freezing air from the Arctic Arctic to intrude on the warmer mid-latitude regions. So this means that even as the Earth, right? Earth warms on average and climate change, it may lead some places to see some more extreme cold spell during winter, right? So now the polar jet stream sits in the troposphere, the lowest layer of our atmosphere, where most weather happens, right? So it is characterized by a belt of wind. So that blows, you see, so this is the polar often. So it from west to east, it speeds up to a couple of 100 miles per hour, right? So while it shifts a bit north or south throughout the year, and it is usually stays between the 50 to 60 degrees parallels. So roughly between the Great Lakes and Canada, Northern territories are between France and Norway, right? So the jet streams forms at the boundary where cold polar air, and you see here, and warm mid latitude air try to mix and creating fast moving waves and eddies, right? So, so this is the polar jet stream, right? So now we have discussed this kind of front formation. So this is warm air and front, and this is cold air, right? So and this is 60 degrees, right? This 60 degrees north where jet streams is formed, right? So which is called, what is that? Which is called polar, this one, polar front jet stream, right? Polar front jet stream. So now what happens? Why it is low pressure system? Why? Because so that is not the lower atmosphere, right? So it is the where upper atmosphere. It is upper atmosphere, right? So it can, you see this image, it is observed here this tropopath. So it is in the stratosphere and many times also exceeds stratosphere, right? So it is in the upper atmosphere as we see, right? So that is the first point. And now when you see this warm front, right? Warm front, it is obviously will go up, right? Will go up, this one. And cold front will dominate here, right? Cold front is this blue color, right? So that is what warm and cold air as this is property, right? So what happens? One branch of this actual is going here and subsiding down, right? So this circulation happens in this particular area. So it goes up and this subsidies down on the poles. That is where it is high pressure, right? So, but another branch reaches tropopause and it goes up, goes to upper atmosphere circulation. So, which is warm air in nature in context to polar area, this 60 north degrees, right? So this warm air, which is relatively warmer than what you have cold air in the lower troposphere or atmosphere, right? So this warm air obviously rise up and it will go the polar vortex belt. So where it will starts doing this circle, right? Or whirling action. So due to Coriolis force, it means strongest where at the poles. So if Coriolis force is strongest at the poles, that warm air that rises up will start rotating counterclockwise, right? Counterclockwise. So in the northern hemisphere, right? So that is how this polar vortex is formed, and that is important, right? So now what happens here? The formation of polar vortex is that warm front that rises up in the upper atmosphere, and one branch is actually subsiding down, right? So the tropopause is the dividing the line. That's why some are get confused that even if it is in North Pole, why this low pressure? So this low pressure is because of this warm air front. That warm air front goes that goes up there, right? And in context, so this area is actually relatively more warm because the ground area is far cool. So relatively it is warmer. So that's why it is low pressure, right? And where is this low pressure is sitting? It is sitting where? On the lower atmosphere, which is high pressure, right? So this is the polar front jet stream, which keep binding it, right? So now, what is fixed to this pole and why is not moving here and there away from the pole? So just wait. Wait. Right. So you should remember here, there is a guard, right? There is a guard. So there is a gate. So what is that? This is, sorry, this one. So this one, right? So it's called polar front, right? So polar front jet stream. So it is like a guard. So it is like a gate, right? So which does not allow this polar vortex to move away. So it is fixed in this particular zone, right? So, but remember, at times when this guard, so this guard, this polar front guard is sleeping. What happened is that, for example, in our apartment or something place or office, so or any other place or our university, the night duty guards, when they are sleeping in duty time, what will happen is there? Thieves or sneaks into those areas, right? So when this weekends, so remember jet streams also weekends at certain time period, okay? Certain time period. So that is when this polar um, vortex gets time to actually intrude into certain areas where you find difficult in the Midwest US, in the Canada, where lots of cold winds and negative temperatures are there, right? So that is the polar front jet. It's called like gate, okay? Now you see here. So you observe these two diagrams. So when you have stable polar vortex and you have strong jet stream, so it means these positions are fixed, right? So this is weak jet stream and this is strong jet stream. Okay, strong jet stream. So it is there clearly on the northern pole, right? Northern pole, and it is now guided or bounded by this guard, right? This guard. So that is strong jet streams. So this is the normal situation, stable situation, right? This one. Okay. So, but at times when there is weakening, there is weakening. You see here in the jet stream, when this is loosening up here like this, okay? Like this arrows. So because you understand that there is a continuous north and southward shifts, right? Of the insulation and temperatures will shift, right? So accordingly, pressure will also shift. And remember, jet stream is formed because of the drastic difference between these air masses, right? These air masses. So because of that, this also weakens, right? Weakens at times, and when it weakens, what happens? This cold air moves like this, okay? This arrow, cold air moves where? Southward. This is south, right? This is south and north, okay? Southwards that you see in this particular area, loops, right? So that waves called Rossby. R-O, R-O, S, R-O-S-S-B-Y. So these, these one. So these areas, okay? These waves are called Rossby waves. So when these Rossby waves are weakened, right, it cannot contain this particular area, right? And it starts going down. So, and that is when there starts a problem, and that is where, because of this polar vortex oscillation, right? So according to this Arctic oscillation, as we say, it starts happening, right? So this is where it impacts the this land area. You see here this land area. So this entire Canada and Midwest US, it had lots of freezing temperatures, and beyond freezing temperatures, that leads to what happened? Lots of trouble, right? So now you see, so the polar vortices are weakest during summer. You see here, this is the weakest, right? And strongest during winter. Okay. So remember, jet streams also is stronger in where? Winter. Okay. So, and it is weak during this particular time period when you have summers, right? So what will happen? Obviously, when you have weakening and again strong thing happening there. That is a fluctuation. There is an oscillation, right? So you see here, during this anomaly, during fluctuations, so this expands, right? You see here, this expands, and many times you find that due to this weak jet stream, there is a cold air, right? There is a cold air. So that rushes from this polar vortex, creating these small worlds in particular areas, right? So these small worlds that are entering these entire anomalous systems, that is leads to lots of trouble in the this land areas, which is dangerous in terms of situation, right? So this is the polar vortex, right? So now we are going to another thing that is associated to this polar vortex phenomena, that is ozone depletion. Okay, ozone depletion. So now, the polar vortex is largely in where stratosphere or and remember, stratosphere has maximum concentration of this ozone, right? So what happens in the Antarctica polar vortex? So let's understand the chemistry, right? The chemistry of the Antarctica polar vortex has created severe ozone depletion. What is that? Severe ozone depletion. This one. Okay. So remember, Antarctica has lots of ozone holes, as we know, right? All of you know about that? Antarctica has lots of ozone holes, right? So the nitric acid in polar stratospheric clouds. Now remember, these polar stratospheric clouds have nitric acid composition, right? So it reacts with what is that? Chlorofluorocarbons to form chlorine, to form chlorine formation, right? So if you see here, what is happening? You see here, the 70 degrees, right? 70 degrees south, that is close to a pole, right? Close to pole. So you find chlorine here, right? This chlorine. So chlorine concentration actually from up to here increasing, right? Increasing. So what happens? The chlorine concentration build up during the polar winter, right? Polar winter. So in the polar winters, chlorine concentration rise, and due to this ozone destruction, right? Due to this ozone destruction, it starts happening when there is sunlight that returns in spring, right? So these clouds can only form at temperatures which are below -80 degrees centigrade. So remember, when it reaches that acute winter temperatures of -80 degrees centigrade, right? So that is when this chlorine composition leads to this depletion of ozone, right? So next, and since there is greater, right? So greater air exchange between where Arctic and the mid latitude and ozone depletion at the North Pole is much less severe than at the South Pole, right? So Northern Pole has lots of what mixing of air because of this, right? So land and ocean distribution. So but because so much of land area is not available in southern polar nearby, right? So not much of exchange of air happened. So mostly that concentrated air in the polar vortex, it remains there. It does not, right? Does not change. So as it changes in the northern hemisphere. So that is why due to this persistently remaining chlorine. Okay. So actually it leads to more ozone depletion in the southern portion than in the northern portion. Right? So now, so accordingly, the seasonal reduction of ozone level over the where Arctic is usually as ozone dent, right? So remember there are two terms in southern hemisphere. So that is in the Antarctica belt. So that is called ozone hole, right? Ozone hole. So because it is larger, while it is just called a dent ozone or ozone dent. So dent in the northern hemisphere or in the Arctic belt. So that is in the main region, right? So now you remember that how this polar vortex phenomena is also related to ozone depletion, and that is another important point. So this is the polar vortex phenomena. It's important, its creation, right? Now you see here. So we are going to ozone depletion process. How to ozone depletion processing is there, right? So now you see here, you see step by step. First one, this one. So this one, this is the first. I already wrote here. The ozone depletion process begins when these chlorofluorocarbons and other ozone depleting substances, that is ODS. So those are emitted in which place? Into the atmosphere. Use here, right? And second one. So this is the process. First process is the ozone depletion process begins with uh, when chlorofluorocarbons, right? Chlorofluorocarbons and also other ozone depleting substances. Those are, it's called ODS, ozone depleting substances. So those are chlorofluorocarbons and ODS. So those are emitted into the atmosphere. And next, what will happen? And second point, this one. So winds efficiently mix the troposphere and evenly distribute the gases, these gases. Sorry, right? The chlorofluorocarbons are extremely stable and they do not dissolve in rain, right? So after a period of several years, this ozone depleting substances molecules reach the stratosphere. About how many kilometers? 10 kilometers above the Earth's surface. Okay. 10 kilometers. Next one is third process. In third point, the strong ultraviolet light breaks apart the ODS molecules. The chlorofluorocarbons and hydrochlorofluorocarbons, and also what is that? Carbon tetrachloride, and also methyl chloroform, and also other gases. So those are release chlorine atoms, right? Chlorine atoms. This one. And halogens, and also methyl bromide. So release bromine atoms, right? And next point is fourth one is it is these atoms actually destroy ozone, right? So not the intact ODS molecule. So it is estimated that one chlorine atom can destroy how much? Over 1 lakh ozone molecules before it is removed from the stratosphere. 1 second. So now, fifth point. So you got my point? So the one chlorine atom. So one chlorine atom can destroy how much? 1,000 ozone molecules before it is removed from the stratosphere, not atmosphere, stratosphere, right? So the ozone, next fifth point, right? So fifth point, what is that? Depleted, right? So depleted ozone allows more ultraviolet, this one, ultraviolet radiation to pass through the atmosphere. And sixth one is, you see here. So some ODS, ozone depleting substances, including chlorofluorocarbons and hydrofluorocarbons. It's called HCFS, right? And carbon tetrachloride, and also methyl chloro. So these are released what? Chlorine atoms. So other ODS includes including halogens and methyl bromide. So those are released. What is that? Bromide, right? Bromine bromine atoms. So it is these atoms that actually destroy what? Ozone. So not the intact ODS molecule, right? So you see here. So it is estimated that one chlorine atom, this one chlorine atom can destroy 1 lakh ozone molecules before it is removed from the stratosphere, right? So the biggest problem was chlorine from a man-made compound. It's called chlorofluorocarbon, CFCS, chlorofluorocarbon. So on the ground, these chlorofluorocarbons are not harmful, but once they float up to the stratosphere, the sun them down into chlorine, right? So you got fine. Right. So now you see here, So they bind with ozone to make oxygen. This one. Sorry. Oxygen and chlorine monoxide, then the loose oxygen atoms bump the chlorine atom out, right? Chlorine atom out and freeing it to destroy more ozone molecules, and that causes a chain reaction, right? So the long lifetime of the chlorofluorocarbons, it is a big part of the problem. So they live anywhere between 50 to how much? 50 to 150 years in our atmosphere, right? 50 to 150 years. So you see here, these are the molecules. Okay. In 1987, the ozone level has dropped by how much? 50%, right? 50%. So this growing threat lead to some of the fastest collective action on climate we have ever seen. Okay, we have ever seen. So here, this is in the year of 1987. Okay. So after the chlorofluorocarbons ban, when we began using hydrochlorocarbons, so these hydrofluorocarbons don't deplete the, does not deplete the ozone layer, but they are a potent greenhouse gas that contribute to which one? Climate change, right? So in year um, 2016, right? So 2016, the Montreal Protocol was amended to include hydrofluorocarbons, and now they are being phased out too. So, but they are only one part of a larger issue. So I will tell next class and tomorrow Montreal Protocol. What is the Montreal Protocol, right? So now, the colder temperatures over the polar regions have been shown to promote ozone depletion, right? So while warmer temperatures lead to increased ozone. So years with warmer temperatures generally had smaller holes, while colder temperatures had large holes. You got it? So the warmer temperatures had smaller holes, right? And while colder temperatures had larger holes. Okay, you got my point? Right. Now you see here. So this is the important question. So why ozone hole especially is in Antarctica over the South Pole? Why? Anybody tell me why? Why ozone hole is in Antarctica only? Anybody? Okay, right. So in the year 1995, some of the scientists discovered a massive loss of ozone layer in over Antarctica. This one, okay? So because the one factor is the chlorofluorocarbons. So these are producing the reactive reactive chlorines, right? Reactive chlorines. So that breaks down ozone. But where do those chlorofluorocarbons come from? Well, they are all over the world, right? So they come from mainly which one? Air conditions. This is very important. Okay? air conditions. So they are all over the world, all over the earth. There are chlorofluorocarbons in the atmosphere. So that includes over to us, right? So the very low winter temperatures in Antarctica stratosphere cause what is that? Polar stratospheric clouds. That is called PSCS, polar stratospheric clouds, right? So that is to form. So special reactions that occur on these polar stratospheric clouds combined with the relative isolation of polar stratospheric air allow chlorine and bromine reactions. So that is to produce, what is the produce? The ozone hole in Antarctic springtime, right? So now you see here the formation of ozone hole in Antarctica has been an annual occurrence and it has been recorded for the last 40 years, right? So what is the reason? Human-made chemicals. Human-made chemicals migrate into the stratosphere and accumulate inside the polar vortex. So it begins to shrink in size as warmer temperatures dominate, right? So the Antarctic ozone hole, one of the deepest and largest gap in the ozone layer in the last how many years? Last 40 years. So now it has closed. Remember this. Now it has closed. According to um, Raki, so the World Meteorological Organization in January 2021, January 6th, 2021, right? According to WMO, World Meteorological Organization, it has closed. So the annually occurring ozone hole over the Arctic had rapidly grown from mid-August, right? When mid-August and peaked at around 24 million square kilometers. So one of the largest to fare in early October 2020, right? So the expansion of the hole was driven by a strong, stable, and cold polar vortex and very cold temperatures in the stratosphere. So the same meteorological factors also contributed to the record in which year 2020 Arctic ozone hole, which has also closed, right? Which has also closed, right? So a polar vortex is a wide expanse of swirling cold air, a low pressure area in polar regions. During winters, the polar vortex at the North Pole expands, sending cold air to southward. So an ozone hole is the thinning of the ozone layer boosted in size by colder temperature. So at the temperatures high up in the stratosphere starts to rise, the ozone depletion slows, the polar vortex weakens and breaks down. So by the end of December, the ozone levels return to normal. So this time around, however, the process took longer. So the 2020 Antarctic cold was unprecedented as the polar vortex kept the temperature of the ozone layer cold, preventing the mixing of ozone depleted air above Antarctica with ozone-rich air from higher latitude, right? So now you see some of the picture variations of the ozone hole. So remember, 2019, the ozone hole is the smallest on the record. Smallest, remember, smallest, okay? Smallest on record. So the abnormal weather patterns in the upper atmosphere over Antarctica dramatically limited ozone um, um, depletion in September and October 2019. It resulting the smallest ozone hole since when 1982. So that is NASA and NOAA. NASA and NOAA scientists are reported. Okay, so the annual ozone hole reached its peak extent of 16.4 million square kilometers or 6.3 million square miles on September 8, 2009, and then shrank to less than 10 million square kilometers, right, for the remainder of September and October. So during years with normal weather conditions, the ozone hole typically grows to a maximum area of about 20 million kilometers, right? 20 million kilometers. So it's great news for ozone in the southern hemisphere. It said Paul, see here. Hmm. Paul, Paul, Paul Newman. So the Paul Newman, he is a chief scientist for Earth Sciences at NASA and Goddard Space Flight Center. So, but it's important to recognize that what we are seeing this year is due to warmer stratospheric temperatures, right? So it's not a sign that atmospheric ozone is suddenly on a fast track to recovery, right? So the large and deep Antarctica ozone hole in 2020, it persistent cold temperatures and strong circumpolar winds supported the formation of large and deep Antarctica ozone hole in the year of 2020, right? And it is likely to persist in November, right? November. Okay. So on 20th September 2020, the annual ozone hole reached its peak area. How many kilometers are 24.8? This one. Okay. 24.8 million square kilometers. So roughly 3 times the size of the continental United States, right? So some of the scientists also detected the near complete elimination of ozone for several weeks in 6 kilometers high column of the stratosphere near the geographic South Pole, right? So now what are the reasons for the ozone hole? So the ozone hole has developed because people have polluted, right? Polluted the atmosphere with chemicals containing chlorine and also bromine. So the primary chemicals involved such are chlorofluorocarbons and bromine and also other related halogen compounds and carbon tetrachloride and also nitrogen oxides, right? So the chlorofluorocarbons in particular have been used for a wide range of applications and including refrigerators, and also air conditioners and foam packaging and making aerosol spray cans, right? So these chemicals, right? These chemicals are so inert, so they are able to stay in the atmosphere for long enough to be carried upward to the stratosphere where they can damage the ozone layer, right? So that actual process by which chlorofluorocarbons destroy ozone are complex and require certain weather conditions to exist, right? So now, what are the ozone depleting substances? So ozone depleting substances, it's called ODS, right? ODS, ODS, ODS. So those are generally contain, what is that? Chlorine, fluorine, and bromine, and carbon, and also hydrogen. So in varying proportion, and those are often described by the general term halocarbons, right? Halocarbons. So the chlorofluorocarbons and carbon tetrachloride and methyl chloroform, so those are important human produced ozone depleting gases, so that have been used in many applications, like including refrigerator, air conditioning, etc., etc., right? And another important group of human produced halocarbons is the halones, right? Halones. So which contains carbon, bromine, fluorine, and chlorine. So and have been mainly used as fire extinguishers, right? So these substances are effective ozone depleters for two reasons. So that is, the first is that they do not break down the um, lower atmosphere, right? Lower atmosphere. So they can remain in the atmosphere from 20 to 120 years or more. So unlike the most chemicals released in the atmosphere at the Earth surface, the ozone depleting substances are not washed back to Earth by rain or destroyed by other chemicals, which means they drift up into the stratosphere, right? And second is that they contain either both chlorine or bromine, right? Chlorine and bromine, and thus help the natural reactions, so that destroy ozone. Chlorine and bromine destroy ozone, right? So once they reach the stratosphere, the ultraviolet radiation breaks up these molecules into the chlorine, right? For example, from chlorofluorocarbons and methyl chloroform are carbon tetrachloride or bromine, right? So which in turn break up to ozone, okay? So what are the ozone substances? Now, ozone depleting substances are chemicals that destroy the Earth's protection ozone layer, right? So they are include chlorofluorocarbons, hydrochlorofluorocarbons, and hydrobromofluorocarbons, halones, methyl bromide, carbon tetrachloride, methyl chloroform, and bromochloromethanes. So these are the some of the substances are destroy the earth protective ozone layer. And what did we use ozone depleting substances for? So use of these substances, the main uses of ozone depleting substances, including the chlorofluorocarbons and hydrofluorocarbons in refrigerators and air conditioners, and some of the in commercial use, right? And also chlorofluorocarbons and halones in using fire extinguishers, and chlorofluorocarbons and hydrochlorofluorocarbons in foam, and chlorofluorocarbons and hydrochlorofluorocarbons as aerosol propellants, as using aerosol propellants, and also methyl bromide for using for fumigation of soil structures and goods to be imported or exported, right? So now, what are the chlorofluorocarbons? So the chlorofluorocarbons are a group of chemical substances. So that contain one or two or three carbon atoms, right? So and at least one atom is each of chlorine and fluorine. So the chlorofluorocarbons were first developed in the year of 1920. 1920s to replace sulfur dioxide as a coolant gas. So in the 1930s, so they began to replace ammonia for cooling uses. So their non-toxicity and non-flammability and stability and heating absorption effectiveness, those are earned them early respect as wonder chemicals of the this 20th century, right? So in the late 1940s, they began to be used as the what what is that? Propellant in aerosols. So this use hit its peak in the late 1970s. So when the chlorofluorocarbons was identified as an ODS. ODS means ozone depleting substances and also aerosols. So it became the main target of public actions. So the chlorofluorocarbons were also used in the production of, what is that? Production of packaging and insulating and also other forms. So in 1980s, they were widely used as coolant in refrigerators and air conditioners. So as solvents in degreasers, right? And cleaners and to dilute sterilant gas mixtures and also as blowing agents in the production of, they are using production of farms, right? So the manufacture and use of chlorofluorocarbons in industry, it has been severely curtailed following the Montreal Protocol, right? Montreal Protocol. So they have been almost completely phased out in developed countries. So with remaining uses limited to meter dose inhalers. And starting in 2010, in developing countries need to completely phase out chlorofluorocarbons, right? And now, how long they stay in the atmosphere? It means lifetime, right? So the chlorofluorocarbons, you see, so this is the table, lifetime period table. So this is HCFC 22 and HCFC 123 and HCFC 124 and HCFC 141B and 142B and 225CA and 225CB. So these are some of the lifetime periods, and chlorofluorocarbons are hydrochlorofluorocarbons, right? So now I will stop after here. So I will take the class and tomorrow. Okay. So any doubts in this PPT? Rakhi, Bhagyaraju, Bhavani, Kumari, Janaki Kumari. Any doubts? Right.